Okay, so we have base ionization equilibria versus the acid ionization equilibria that we did earlier. And what we find, let me show you the relationship between them. We have a weak acid plus water goes to H3O plus, and the conjugate base of the acid. That's what A minus is. And you can see that what happens is of the two, the acid is the stronger acid than water. Water can act as an acid or a base, but in this case it acts as a base and it accepts an H+. Ka is then the concentration of H3O plus times the concentration of A minus. You've seen this many times, over the concentration of HA. Now, if we have a base, well then it's up against water. A base then will allow water to act as an acid. It gives up an H+. The H+ goes in the opposite direction. It creates the conjugate acid of the base and OH-. So an acid creates H3O+, base creates OH-. We shouldn't be surprised about that. We know that from the definition. And then the Kb, we'll call it Kb because we're dealing with a base. Still just K, it's just, or Kc, it's still just the equilibrium constant, but we label it with a B to indicate that it's something special. We're dealing with bases. But look at the format here. It's exactly the same. So we're going to use an ICE table. We're going to use that ratio to see if the approximation holds, and the math will be exactly the same. And that's why we don't spend a lot of time on this, because we already know how to do a weak acid type of problem. The weak base one is almost exactly the same. We just have to keep in mind that we're dealing with a base, so there's a couple of little differences. The one that is most noticeable is that we create OH-. So when we create OH-, we'll be able to easily find POH, but what I'm asking for is pH. I might ask for POH, but most of the time, even when dealing with bases, you want to deal with pH. Because you don't like to go back and forth, or you shouldn't go back and forth between those scales. Sometimes it can get a little confusing. You want to leave pH alone and know that if it's a very low pH, it's acidic, very high pH, it's basic. Okay, so we do out the problem, minus x plus x plus x, same thing. And then Kb is the concentration of ammonium ion, which is the conjugate acid of ammonia, OH- over the concentration of ammonia. So this is x squared, 0.167 over 0.167 minus x, which is equal to the Kb of ammonia, which is found in the table. It's 1.8 times 10 to the minus 5. Notice this equation is exactly the same format as the weak acid one. So we solve it in the same way. First we determine if the approximation holds. 0.167 divided by 1.8 times 10 to the minus 5 comes out to be 9,277. Did that earlier. But it's about 10 to the minus 1 divided by 10 to the minus 5, so we should expect it to be huge. It's definitely greater than 100. And you say, well, does it hold for bases? The test we're doing is a mathematical test. It doesn't matter how we got this equation. Even if we just made it up, we have it, if it's not related to any chemical process. The math tells us that if this approximation does hold, or this ratio holds, then if we get rid of the x, we are definitely going to have an answer that is less than 5% off. And because it's such a large number here, it's going to be probably much less than 1% off. So now we have this expression, and we have 1.8 to the minus 5 times 0.167, and then to the 0.5. And so x is equal to 0.00173 molar, and that is the concentration of OH-. Now the negative log of that is going to be POH. This is the only thing that really gets students, is because I like to stick with pH. Even though OH minus, the concentration of OH minus will get us to POH easier, let's see, so we have negative log of 0.00173, and the pOH is 2.76. Now this should stop you if you forget to change the pH. This should stop you because you have 2.76. That should be, if that was pH, that would be a very acidic solution. Since it's pOH, it means it's a very basic solution. So pH is going to be 14 minus 2.76, so that is 11.2. That's our answer right there. Okay, anything else? And then the equilibrium concentrations, I wanted all of those, so we know that the concentration, just put it over here, so we have OH minus, so this guy is OH minus, and it's also the concentration of NH4 plus, and then, and I've done this before where it doesn't seem like I want to finish the problem, but normally I'd only ask for the pH, but here I want to ask for every single thing, so we cover all of our bases just in case I do ask you for the concentration. It does come up on the exam. I don't want to say I always give just pH. And there it is for ammonia at equilibrium. Okay, let's try another one, another base. So what is the pH and pOH of 1.88 molar hydrazine? Okay, now hydrazine is N2H4, and that's in your table. And a lot of people would have trouble with this because it looks so unusual. Just make that B. It's a base. If you're unsure if it's a base, you'll have your Ka and Kb tables. If you find it in Kb, you know that it is a base. And then you have Hb plus and OH minus. Initial change equilibrium. We have 1.88 molar of the base, minus X, plus X, plus X. 1.88 minus X, X and X, X squared over 1.88 minus X. And then we look for the Kb for hydrazine, and that would be 1.70 times 10 to the minus 6. And you should be able to see that this is about 1, a little bit more, divided by 10 to the minus 6. So that ratio should be around, these two numbers are almost the same, so it should be around 1,000,000. So the approximation does hold. So X squared and then we take the square root of that. So X, I shouldn't do that out. X is the concentration of OH minus, and that is 0.00179 molar. It's almost the same as what we did. I think that's almost the same as the last answer. That's okay. It's just by chance. So the pOH is equal to the negative log of 0.00179. So negative log of 0.00179 gives us a pOH of 2.75. And then a pH equal to 14 minus 2.75. And I think I can do, but I want to make sure I get the rounding right. So that is going to be 11.3. So there are the two answers.